Hello everybody, welcome to the World of Control channel. I'm Mohammed, and in this video I want to design a SMC controller for our system of inverted pendulum on a cart that we modeled in the previous video. Make sure that you subscribe this channel because I will make a lot of videos about modeling different systems and designing different controllers. So let's get started. As you can see in the previous video, we modeled the dynamics of our inverted pendulum on a cart, and we want to actually simulate this sliding mode controller that we can see the relationships and the formulas of that in this PDF here. Okay, first of all, I need to apply a force on our cart. So I want to apply another force along the x-axis of our cart, and I want to apply it on the center of mass of that. Because of that, I will open the cart's block and click on frames, and after that new frames, and I will click on at center of mass here, so we can have a frame on the center of mass of our system. I will rename it as CG, and now we can see that we have our center of mass frame here. We can now connect our force along the x-axis to center of mass of our car. For controlling this system, we need to have the actual theta and actual position of the car. So I will import a transform sensor, and I will click on it and say that I want the x translation of the center of mass of this system with respect to the world frame. And this signal is the x signal of x real. And also I need another one to actually sense the actual theta. So I have to click on rotation sequence and change this measurement frame to base and change this to ZXZ. And I need a demux to actually de-augment this signal here. I need a PS converter to change the type of my signal to Simulink signal, and I want to measure the amount of rotation of F1 frame on pendulum with respect to F2 frame on the cart. Okay, this first signal is the theta that is rotated around the z-axis, but we do not need other signals here, so I will use two terminators to actually block these two signals because we do not need them. This is the real theta, so I will rename it to the real theta, and I use another PS Simulink converter to have my real X. Okay, now I want to import constant blocks to actually make my desired X and desired theta. I will make them as 0 and 1 for the first time, and I need some block to make my errors. Okay, now I need to make my errors. This is error of theta, and this one is the error of position. Now I will use the mux block to actually augment these two signals and make the error signal, and I need to make the derivation of this signal. This is error dot. I need another constant block to actually import my lambda. My lambda has to be a diagonal matrix. For example, for now I will import 5 and 5 for both signals, and I need a product block to actually multiple my error to my lambda, and we need to change this multiplication to matrix here. We need another sum block to sum these two, and this is my sliding surface. As we can see, this is my sliding surface here. Now we need to have this tangent hyperbolic and to multiple our sliding surfaces to our u stars. Actually, I will make them as minus negative 50, and this signal is our controlled input signals. I need another Simulink PS converter, but this is force. The unit of this is force. Because of that, I need to change this input signal unit to Newton. But this one is torque, and we need to make this Newton meter. I need to use demux here to actually demux my signals. The first one is my tau signal, and the second one is my force signal. Let's show the results on scope 2. So I need to import scope and change some settings here, such as the colors of our system of plots. I will say that I want to import two signals to this, and I want you to show them into two figures. I need to compare my actual signals and desired signals, so I will import my real x and desired x, and also my real theta and desired theta. Theta desired, real theta, x desired, and this one is real x. Okay, and now let's run this simulation to see how it works. Okay, we can see that our system is controlled on 1 meter, and the first one is, let's make the legend on to see which one is our real x and desired x. We can see that the orange signal is our desired x, and our blue one is our real x. And also in the in this plot here, we have our theta desired and real theta. We can see the animation of our system also. We can see that it is controlling very well. So let's change the references here to see how it works. Let me change this to pi third to see if our system is controlled very well. Oh, we can see that we have some overshoots, but our system is very controlled where our pendulum is in 60 degrees and the position of our cart is on 5 meters here. Let me see our scope. We can see that with the overshoot we are controlling both position of our cart and the theta. Let's change the signal to I need my pendulum to uh, track a sine wave signal. Let's change this to pi divided by 6 and run the simulation to see if it works. Okay, we can see that our pendulum is rotating, oscillating actually, but the position of our cart is on 2 meters. Let's also watch out our scope to see if our system is working well. Oh, we can see that x is controlled on 2 meters here and theta is actually oscillating in the direction of in the actually trajectory that we wanted. Uh, we can optimize the control coefficients, control parameters by using different other algorithms. Make sure that you subscribe this channel. Thank you very much.